And then once you have the y's with the dy and the x's with the dx's, then you just integrate both sides normally. And you get your equation with x's and y squareds and all sorts of things. So let's look at the next one. So I got dy dx equals sine x y squared. Since I have x's and y's in my derivative, I want to separate my x's and my y's. So I'll move my dx over and my y squared to the other side. Now, moving the y squared to the left side would mean dividing by y squared, which makes it a y to the negative 2. And then from there, you integrate both sides. And again, if you wanted to integrate this side and go directly to just 1 plus c and skip this step, I'm perfectly fine with that. And you could leave it like this, but you might want to get the y by itself. And if you wanted to get the y by itself, then you'd have to multiply both sides by y, divide both sides by the cos x plus c. And once again, if you look at like little intricate things in here, technically, if I divide it by negative cos x plus c, do you see that technically there should have still been a negative on the top and a negative with this cos? Technically. Right? Because if I move this y up over here and move this whole thing down to the bottom of the fraction over there, there would still be a negative with 1 and negative with cos. And if I wanted to get rid of those negatives, I could factor out a negative, which technically would make the c a minus c. But because it's a c, they're sometimes not worried about that. So just some, with the plus c, you've got a little bit of leeway because it's going to be any number anyways. So sometimes signs change on it. I think for sanity's sakes, I would try to keep it what it should be all the way through. So try this one. Try this one and the next one as a warm-up. Some of you have done them already, I see. That's great. If you've done them, turn to the next page. And you can work on those ones while you're waiting. All right, so we separate our x and our y. We get a 1 over y, which gives us a natural log of y. And this would be fine if you left it like this. But there's going to be some questions where you're going to be asked to solve for y, or it could be multiple choice where they rearrange this. Now, if I have natural log of y by itself, I can change it to exponential form. Remember, the base of the natural log is e. And so I can do e to the x squared over 2 plus c. And then I can use some of my exponent laws, right? If you're adding exponents, that would have been the same as multiplying them beforehand. Right? If you have the same base with the exponents, your exponent law says you can add the exponents. So now, a lot of calculus takes all of those rules that you learned from grade 9 through 11, like adding fractions. We've had to unadd fractions. Now we're undoing exponent laws. And so you'll see in a multiple choice that the final answer looks like this. And you're like, how did they get that c in front? Well, technically, when I break this up, this x squared over 2 plus c is an exponent to e to the half x squared times e to the c, because that's just undoing your exponent rule. E to the c is a number. So we can make that our new C. Technically, if I was wanting to be really appropriate with notation, here I had a C1 and here I had a C2. I put them together and I got a C3. This would still be the C3. This would still be the C3. And then when I put the E to the C3 together, that's my C4. I've changed C 4 times. But on a multiple choice question, they would just say, well, here, this is the final C that we got. And this is where it shows up. So again, there's a lot of, and you've seen this, and you'll see this on the exam, you might be able to do the first part of the manipulation of a multiple choice question, but then there's a bunch of algebra that needs to be done to make it match up. So it's just important to see all of those algebra tricks along the way. And here's our last one. So I want to get the x's by itself and the y's by itself. So I have to do a little bit of work, and it's going to be very important that we change things to multiplication, because if you change things to multiplication, you can move things to either side, so you can do the integration separately. If you just add and subtract, we've never done an integral of dy plus y. That really doesn't make sense, because if you integrate that, well, you can integrate with respect to y, but then the plus y doesn't have any variable connected to it. So we always change to multiplication, and then we can get that y plus 2 over to the other side. And from there, simple integration. We get a natural log again. So if I was numbering things here, this would be my C3. If I change it to exponential form, this is still my C3. Then this becomes C4. So find the solution to the differential equation. Again, the language here, when they're asking for a solution to a differential equation, they're looking for you to integrate one step up and find the equation. We've got our differential equation, dy dx equals xy squared, and we have an initial condition. We know that when x is 1, y is 1. We have the point 1, 1. Can we separate it? Well, first you'd have to use your exponent law, so that becomes x squared, y squared. It's multiplication. That would allow you to separate them. Integrate on both sides. And I'm okay if you skip right to this step and just put a plus c once. Now we know that when x is 1, y is 1, so this allows us to solve for c. and you get negative 4/3. So now we could write out, our particular solution. And again, if the multiple choice had the y by itself, you could rearrange and get y by itself. Now, sometimes just for fun, because I know that you guys all do math just for fun, right? All the time. When you get an answer like this, and you got y by itself, you could do the derivative of this easily. It's just your regular derivative rules. Maybe you use your quotient rule. Maybe you change the bottom to an exponent of -1 and use a chain rule. But you could do the derivative of this, and you could get dy dx. And if you did the derivative of that and got dy dx, does it make sense that your derivative would just have x's in it? Notice our original derivative had x's and y's in it. See if you can see that they match. Because my original derivative, if I replace this y with the actual equation for y, do they actually match? Play around with that algebra. And in playing around with that algebra, of course, you're going to improve your algebra skills. Also, it's really nice because you can check your answer in the end to see if it works. Again, it starts with find the solution. So if you have a differential equation, you are trying to find the solution. And in this case, it's listed it as y equals something. So in this solution, they do want you to simplify to get y by itself in the end. This initial condition tells us we have that when x is 2, y is 1. Can we separate our x and our y's? Easy integrals with a plus c. Plug in x is 2 and y is 1. Solve for c. And then, can you get y by itself? Yes. By square rooting both sides. So try the last one. I'll put up the answer in a second. I'll put up the answer and you can look at it. When you're ready. So this is the typical place that we get to. And then if we want to get the y by itself, we're going to have to use our exponent laws. I think I like this one best. But of course, if it was multiple choice and they did some fun rearranging, you could play a lot around with your exponent laws there. If it was long an answer, I'd definitely stop at that first one.